Okay, this is problem 2009 E3 from the AP Physics E&M exam. The first part is asking you to derive an expression for the magnitude of the EMF generated in the loop seen over here. You have two light bulbs with an equal resistance, and you have this length of the square. And you have this B field, which depends on the equation B of t equals AT plus B, where A and B are constants. By Faraday's law, we know that EMF induced by the flux is equal to the number of loops times the change in flux with respect to time, absolute value. So, since there's only one loop, you can just say that n is equal to 1. Okay. And so, since we're looking for the rate of change of flux with respect to time, we need to also take the derivative of this equation. So, basically we would do this. EMF would equal area times change in magnetic field with respect to time. So you could literally just take that down here and plug that in. So you would get A d over dt AT plus B. So if you're taking the derivative, it's simple. This would just cancel out since it's a constant, and the rate of change of AT with respect to t is just A. So we get that EMF would equal A, big A, little a. And since this one is area, and this is a square, we know that this is literally just AL squared. Alright, now to part B. And let's label A. So part B, part I of part B actually, is asking you to determine an expression for the current through bulb 2. This one right here. So that should be simple enough if you already know the EMF and you know the total resistance of the series circuit over here. You simply use Ohm's law and figure out that the current is equal to the EMF over the resistance, which in this case is equal to AL squared over 2R initial. Part 2 is asking you to find the direction of the current itself. Since we know that the magnetic field is increasing and it is going into the page, we know that the loop will have to generate a magnetic field that would oppose this change in magnetic field. So it would go the other way, and using the right-hand rule, we know that the current would go this way, which is counterclockwise. So part C is asking us to find the power dissipated by light bulb 1. We know that to find the power from a resistor, we need to use this equation, where I is the total current, but R is actually just the resistance of that one resistor, which is light bulb 1. So we can plug this in here, and simply multiply it by the one resistor. So obviously these cancel out, and the answer is that. So part D changes the scenario a little bit. So we have this original square with the field in it, same strength, bulb 1, light bulb 2, but outside the field there is one more area added with light bulb 3. So the question is asking whether or not the brightness of bulb 1 changes, and if so, how much does it change? We know by looking at this that since the area of the magnetic field never changed and the equation is still the same, that means this loop over here does not add any new flux. So the only real change that this actually gives us is that it lowers the resistance in this loop. Essentially, all the current would have to go through here, but now it actually gets to split up. So this one essentially makes the current over here higher. So even though it doesn't add any flux to the circuit, light bulb 1 actually becomes brighter.